everyone, welcome to Science Within Voice. In today's video, we'll be talking about sound wave, the Doppler effect, and shockwave. But before we begin, be sure to subscribe for some more great content. Alright, let's go. So first up, we have sound waves. So what is a sound wave, and how do they work? Well, first of all, sound is a longitudinal wave, and a sound wave travels by disturbing the particles of the medium as they move along. The medium for sound waves to travel could be any series of interconnected and interacting particles, so the medium can be solid, liquid, or gas. The source of sound could be any vibrating object as long as it can disturb the first particle of the medium. This object could be the vibration from a chirping bird, the vibration of the vocal cords from people talking, or the vibration of metal from a machine. There are two factors of a medium that contribute to how fast or how slow sound waves travel. First is the stiffness of the object, or how hard is the object to compress using an external force. It's because the stiffer the object, the more interconnected are its particles. And as we explained earlier, sound waves travel through the particles of an object or a medium. And because stiff objects have more interconnected particles, sound waves travel faster through it. Second is the density of an object or medium. If an object is more dense, it has more inertia, and therefore it is very slow to changes in motion, causing the sound waves to move slower. These two factors are taken into account in this formula. V is the speed of sound, rho is the density of an object, and capital B is the bulk modulus of an object. Bulk modulus is the official way physicists measure how stiff an object is. If an object has both a large bulk modulus and high density, usually the large bulk modulus more than compensates for higher densities. So this would mean the speed of sound in solids is almost always faster than in liquids, and the speed of sound in liquids is faster than in gases. Next, we have the Doppler effect. What is the Doppler effect? A while ago, we explained that sound waves travel through the particles of the medium, and that sound waves come from the source of sound. But the source of sound is stationary. What if the source of sound is in motion? What will happen to the waves? Well, if the source is moving in the direction where the source is moving, the waves in front back up, and the waves behind the source spread out. If the source of sound moves toward the stationary observer, the bunch of waves in front will be observed at a higher frequency. And if the source is moving away from the observer, the waves are observed at a lower frequency. Let's put this effect into application. Let's say you are standing beside a highway and a car passes by you very fast. Now it may sound something like this. As you have observed, as the car was moving towards the observer, the car engine was heard at a higher pitch, and as the car was moving away from the observer, the car engine was now heard at a lower pitch. Even if to the driver of the car engine sounded exactly the same the entire time. So that is the Doppler effect. By definition, it is the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. Also keep in mind that the Doppler effect is not limited to sound. It can also be applied to light waves as well, especially in stars. In sound, the frequencies emitted are interpreted as pitch, but for stars, when they move, the light waves are interpreted in color, depending on the frequency interpreted. So when stars move, stars change color. This is known as the red shift. And for the final topic, we have shockwave. In the previous topic, we discussed how the source of sound will affect the waves emitted if the source of sound is in motion. That is the Doppler effect. But what if the source of sound goes really, really fast? So fast that it equals the speed of sound itself. Well, if that happens, aside from having more frequency, the waves in front will keep on adding more and more pressure, and the waves behind will still be interpreted at a lower frequency. But what if it goes faster than that? What if the source of sound exceeds the speed of the sound waves? When that happens, pressure and constructive interference will build up along the sides of the wave. This is when a shock wave is in occurrence. Shock waves are the ones responsible for sonic booms, which sound like this. A common example for objects that create shock waves are jets. When jets equal the speed of sound, they actually meet some resistance because of the pressure building up in front. So jets need more energy to break through what is known as the sound barrier. Just like the Doppler effect, shockwaves are not only limited to sound. Shockwaves can also happen in water. Water waves are quite sluggish, so a boat or even a duck can create shockwaves in water. That's why they leave a cone-like trail when they pass by. And that is it for our video. We hope you learned something new today. And as always, we them boys signing out.